Hello everyone. First and foremost, I would like to thank Department of Physics, Namchi Government College, Sikkim University and Dr. C.P. Khadiwara sir for providing us the platform to make this video for the partial fulfillment of PSC 4th semester. This video is for the Sessional B examination. My name is Alpha Limbu, roll number 19NS0061 and my topic is Lorentz Transformation, Length, Contraction and time dilation. Lorentz transformation. A Lorentz transformation is a mathematical way of relating physical quantities that describes objects between two different inertial reference frames while taking into account the special theory of relativity. The name of transformation comes from a Dutch physicist, Hendrik Lorentz. So, a Lorentz transformation incorporates time dilation and length contraction of a quantity such as time and length. We will now derive the Lorentz transformation equation that basically allow us to make the relation between two different inertial reference frames. So let us suppose we have two inertial reference frame F and F prime. We have two inertial reference frame F and F prime. F consists of x, y and z axis, while F prime consists of x prime, y prime and z prime axis. Time in frame F is given by t and time in frame F is given by t prime. Now at t is equals to t prime is equals to 0, the two forces are superimposed or they are found at same exact position, that is z and z prime lies on same axis, x and x prime lies on same axis, y and y prime lies on same axis. Now basically we want to find the three equations that will allow us to transform the coordinates from one frame to another frame, and to do it we are going to use the equation from Galilean transformation, which is x equals to alpha x prime plus vt prime, y is equals to y prime, z is equals to z prime, where alpha is an unknown constant or alpha is equals to length, contraction constant. Now let us suppose we have a point in frame F and we want to transfer this point or coordinates to the frame F. And so to do it we have to use the equation which is this one from Galilean transformation, and we see that frame F prime is moving with velocity v right along x-axis with respect to the stationary frame F. Here F frame is stationary and F prime frame is moving. This is case 1, and in case 2 we have case 2 we have, so basically we are dealing with two inertial frame, that means our motion is relative. Our motion or movement is relative. Thus we can also say that frame F prime is stationary while frame F is moving with velocity v to the left along x-axis. Here frame F and frame F prime, frame F prime frame, we can say that F prime is stationary while frame F is moving with velocity v along left x-axis, to the left along x-axis. Here we have Galilean transformation x prime is equals to alpha x minus vt, y prime is equals to y, and z prime is equals to z from Galilean transformation. And in case 3, at t is equals to t prime is equals to 0, a light leaves the origin of both references and travels with velocity c. Within frame F, it travels a distance x equals to ct, and while in frame F prime, it travels a distance of x prime is equals to ct prime. Now, we are dealing with frame F. We get ct is equals to alpha x prime plus vt prime is equals to alpha ct prime plus vt prime is equals to, taking t prime common, alpha t prime c plus v, equation A. And from f prime we get ct prime is equals to alpha x minus vt is equals to alpha ct minus vt is equals to alpha t c minus v, equation B. Now in case 4, from equation B, we get t prime is equals to alpha t c minus v by c. We then substitute this into equation number A. We get, substituting in equation A, we get ct is equals to alpha t c minus v c plus v. It implies that ct is equals to alpha square t by c square minus v square, where alpha is equals to 1 by under root 1 minus v square by c square. Here we get the value of an unknown constant or a length contraction constant. Now in case 5, we will have to find out the relationship between t and t prime. In case 5, relationship between t and t prime. Because distance or a length is not the only thing that contract, time also dilates. So there is a difference between time that has elapsed within frame F and the time that has elapsed within frame F prime, because of this special theory of relativity. And in case 5, that's exactly what we are going to find. Here we have x prime is equals to alpha x minus vt is equals to alpha x prime minus vt prime minus vt is equals to alpha x prime plus alpha vt prime minus vt. X prime is equals to alpha square x prime plus alpha square vt prime minus alpha vt. It implies that alpha vt is equals to alpha square x prime plus alpha square vt prime minus x prime. We can rewrite it as alpha vt is equals to alpha square x prime minus x prime plus x square vt is equals to alpha square minus 1 x prime plus x square vt. Now dividing both sides by dividing both sides by alpha v, we get t is equals to alpha square minus 1 x prime by alpha v, here alpha v cancel out, plus alpha vt is equals to alpha x prime minus 1 alpha prime minus 1 x prime by alpha square v plus t prime. Since we know that the value of alpha is equals to 1 by under root 1 minus v square by c square, it implies that alpha square is equals to 1 by 1 minus v square by c square is equals to c square by c square minus v square. So we need to find the t is equals to alpha, putting the value of alpha square, we get c square by c square minus v square minus 1 here square divided by c square v by c square minus v square x prime plus t prime. We get alpha into c square minus c square plus v square c square minus v square, LCM gorda c square by v c square minus v square into x prime plus t prime. Here we get the final equation. We can cut it out like this. We get alpha v x prime by c square plus t prime. T is equals to alpha v x prime by c square plus t. So we were able to derive the equation that basically gives us the time in frame f with respect to time t prime in frame f prime. So this equation t is equals to alpha v x prime by c square plus t prime along with the three equations are known as Lorentz transformation equation. Now we will derive Lorentz transformation. Lorentz transformation derivation. Now let us consider a two frame of references. Consider a two frame of references f and f prime. F and f prime. We have z xy, z prime, x prime and y prime axis. In this case, f frame f is fixed and is stationary, and f frame is moving along the direction of x-axis with a constant velocity v. After some time or after time t, the frame of reference f prime has moved a distance vt. It has moved a distance vt. Now the coordinates in f frame f is x, y and z, and in reference frame f prime we have x prime, y prime and z prime. According to the Galilean transformation equation, we have according to the Galilean transformation equations, we have x prime is equals to x minus vt, y prime is equals to y, z prime is equals to z, t prime is equals to t. Equation number 1. Now differentiating equation 1, we get dx prime by dt is equals to dx by dt is equals to v. We also have c prime is equals to c minus v, where c is the speed of light. And this equation says if a person is moving in a spaceship, the speed of passing light will be c minus v. But according to the postulates of special theory of relativity, the velocity of light remains constant in free space. This suggests that the Galilean transformations are not in accordance with the special theory of relativity, so the need for the new transformation equation is there. However, the equation x prime is equals to x minus vt is in accordance with the ordinary laws of mechanics. So the new transformation for the x coordinates must be similar to this equation. The simplest possible form of this can be x prime is equals to alpha x minus vt. Equation number 2, where alpha depends only on the value of v and does not depend upon the values of x and t. The above equation is linear and x prime has only one value for a given value of x. Now, according to the first postulates of special theory of relativity, observation made in the frame of reference f prime must be identical to those made in f, except for a change in the sign of v, and having the same value for the constant of proportionality alpha. Here x is equals to alpha x prime plus vt prime. Equation number 3. Since the relative motion of f and f prime is combined to only x, we have y prime is equals to y, z prime is equals to z, t prime is equals to t. Substituting equation 2 in equation 3, we get x equals to alpha x minus vt plus vt prime. X equals to alpha square x minus vt plus alpha vt prime. Alpha vt prime is equals to x minus alpha square x minus vt. T prime is equals to x minus alpha square x plus alpha square vt by alpha v, and a t prime is equals to x minus alpha square x by alpha v plus alpha square vt by alpha v is equals to x1 minus alpha square by alpha v plus alpha square vt by alpha v. T prime is equals to alpha t plus x1 minus alpha square by alpha v. Equation number 4. Now we know the value of alpha. Alpha is equals to 1 by under root 1 minus v square by c square. Equation number 5. Now substituting the value of the value of alpha in equation 2, we get x prime is equals to alpha x minus vt. X prime is equals to x minus vt, putting the value of alpha 1 minus v square by c square, equation number 6. And we have y prime is equals to y, equation number 7, and z prime is equals to z, equation number 8. Now we can rewrite the equation 4 as t prime is equals to alpha t plus x 1 minus alpha square by alpha v is equals to alpha t plus x by alpha v minus alpha x by v. T prime is equals to alpha t plus x by alpha v minus alpha x by v is equals to alpha t plus x by v 1 by alpha minus alpha. T prime is equals to alpha t plus alpha x by v 1 by alpha square minus 1. T prime is equals to alpha t plus x by v 1 by alpha square minus 1. T prime is equals to t plus x by v 1 minus v square by c square minus 1 divided by 1 minus v square by c square. Now substituting the value of alpha, substituting the value of alpha in above equation, we get t prime is equals to alpha t plus x by v 1 by alpha square minus 1. T prime is equals to t plus x by v 1 minus v square by c square minus 1 by under root 1 minus v square by c square. T prime is equals to t minus xv by c square under root 1 minus v square by c square, equation number 9. So we now find the Lorentz transformation equation. The equation 6, 7, 8 and 9 are called Lorentz transformation equation. Now, as a result of special theory of relativity, the two important concepts were discovered: length contraction and time dilation. First, we will discuss about time dilation. Time dilation. Simultaneity of event says that the two events that might appear simultaneous to one person and not to another basically means simultaneity is not absolute. We see that since simultaneity deals with time, here arises a question: is time also a relative quantity? Or in other words, does time pass differently to people in different reference frames? Now we will discuss that by doing thought experiment. Thought experiment. Now in this we have two cases. Number one is inside this passive. Inside this passive, here is observer, here is the mirror, observer, mirror, and the distance between them. To the observer, the ship light travels directly across, reflects, and travels back. So the time between event 1, that is light leaving the observer, and event 2, light returning, is given by delta T naught is equals to 2d by c, equation number 1. Here it travels with velocity v. And in case 2, we have stationary observer on Earth. Observer on Earth. We have a passive moving. Here is the mirror, mirror, mirror. Distance and a length between them. A stationary observer on Earth, and this is inside this passive. We are doing a thought experiment. In first case, the observer is inside this passive, and in second case, the observer is at stationary on Earth. Now we see that relative to the stationary observer on Earth, an observer which is not moving, the spaceship is moving. Hence, the light travels the diagonal distance as shown in the figure. Since light travels with identical speed in both cases but travels a longer distance in case 2, the time between event 1, which is light leaving, and event 2, which is light returning, is longer for the stationary observer on Earth. Now here a question arises again: what is the time travel? What is the time travel? Delta T as measured by observer on Earth between sending and receiving the light. What is the time travel? Now we see that c, speed of light, is equals to total distance divided by total time is equals to total distance divided by total time, delta t. Now let v is equals to 2l by delta t. It implies that l is equals to v delta t by 2. Here it implies that c is equals to 2 under root v square delta t square by 4 plus d square by delta t. It implies that c square is equals to 4 v square delta t square by 4 plus d square by delta t whole square. Now c square is equals to v square plus 4d square by delta t square. It implies that delta t is equals to 2d by c under root 1 minus v square by c square. Now from equation 1 we know that delta t naught is equals to 2d by c. So we can rewrite this equation as delta t is equals to delta t naught by under root 1 minus v square by c square. And this is time for moving observer. Always passes slowly, more slowly with respect to the person that is stationary on earth. This is a time dilation. A time dilates. Now we will see length contraction. Length contraction. Length contraction, as we have discussed about the time dilation, one of the many implications of special theory of relativity is time dilation. That is, time will slow down for object moving with high velocity relative to their stationary counterparts, which is delta t is equals to delta t naught by under root 1 minus v square by c square. Equation number 1, where delta t represents the time elapsed in the stationary reference frame, while delta t naught represents, which is proper time, represents the time elapsed in moving frame. We shall discuss about the length contraction, which is length and distance are also not different in different reference frame. We shall discuss that in with a thought experiment, that length and distance are also different in different reference frames. Thought experiment. Here, a spaceship leaves Earth and travels to a distant planet and back. To the observer on the Earth, the time that has elapsed the time that has elapsed is given by delta t is equals to L naught by V, equation 2, which is time elapsed for observer on Earth. Now for the observer in spacecraft, the time elapsed will be less. That is time dilation, and this time is the proper time, delta t naught. Delta t naught delta t naught is equals to delta t under root 1 minus v square by c square. Equation number 3. This is time elapsed for observer on spacecraft. Now, since the velocity of spacecraft does not change but the observer in spacecraft measure less time, then the distance they measure must also be less. Let L is equals to distance measured by observer on spacecraft, then L is equals to V delta T naught is equals to V delta T under root, putting the value of delta T naught 1 minus V square by C square from equation 3, and V L naught by V under root 1 minus V square by C square, putting the value of delta T from equation 2. It implies that L is equals to L naught under root 1 minus V square by C square. Equation number 4. And this is known as the length contraction, where L naught is the proper length. L naught is equals to proper length. It applies to only distances that object travel but also to their length. That is, the length of an object moving relative to a stationary observer is measured to be less in the direction of motion. And this is all we have in this video. Thank you.